No.
You have to take it away, yeah? No, don't worry.
Oh, no, different. So,
Yeah, it's okay. You have to take this out.
yeah, you have to. Okay.
Yeah. Yeah, I had it.
Oh. Strange.
Yeah, it takes some time. Did you test it before?
Yeah, I have tested.
Okay.
Yeah, but so I don't know. Something wrong? Maybe.
Okay,
Yeah.
Finish it.
Yeah, just a reboot.
Okay. Why it is start work? Introducing. So next talk is from Satoru Honda.
Oh,
And the title is Hot Sub-Slab Mantle Beneath the Subducting Pacific Plate, Its Origin and Past Evolution.
Okay. Good afternoon. My name is Satoru Honda from Earthquake Research Institute, University of Tokyo. And this presentation is a result of collaboration with Ismail Zadeh and Morishige and probably Sepelev. I'm not so sure about any. And in this presentation, I will discuss the importance of the hot anomaly in the sub-slab mantle. Okay, these are results presented by Obayashi and others, and they studied the slow velocity anomaly here in the sub-slab mantle beneath the Pacific plate, and they concluded that it's a mainly thermal anomaly, and its magnitude is about 200 degrees. And they also pointed out there is a good correlation between this slow velocity anomaly and 14 kilometer seismic discontinuity. Subsequently, Bagley and others also studied the same slow velocity, and they conclude that magnitude of thermal anomaly is 150 degrees by considering the effect of possible existence of melt. Then we will consider what is the origin of this hot anomaly, possible origins which may explain the hot anomaly close to the called the subducting slab. First possibility is just outside origin. That is, hot anomaly such as plume or plume head came from somewhere. And the second option. Okay. Second is just internal origin, and that is it was basically generated in situ by the internal heating and non-business effects such as viscous heating. So we will consider these possibilities separately. Okay, first possibility is rather easy to understand. Somewhere a hot anomaly went up and then it was dragged by the slab movement, and it came here, something like this. And this model has some merit to explain the observation, as many people believe that phase change expected at 14 kilometers will promote the upward movement of hot anomaly if it comes from below. But in this case, hot anomaly will come from above. So in that case, phase change here will hinder the downward movement of hot anomaly. That may explain the good correlation between the slow velocity anomaly and 14 kilometer seismic discontinuity. So in this model, main problem is where did it come? So we have constructed this kind of a subduction zone model, and we assume some hot material somewhere, and then we will look at what will happen next. So, and in this model, we by imposing the velocity near the upper plate boundary and the top surface, we achieve the plate-like movement. Okay. First, we thought that slow velocity, hot anomaly might come from the first superluminal activity, but it was too radical, and right now we think that it is unlikely. So then I will explain why we came to think so. Okay, these are results, but actually this model, this just right corner model, result of right corner is based on the previous model, by which we propose that the hot anomaly came from the superprion. But in this model, we assume that the temperature temperature of the subducting and overlying slab is a constant temperature. But in revised model, we found that this the old model underestimates the heat transfer between the sub-slab mantle and subducting or overlying slab. So that means if we calculate the revised models, hot anomaly cools too fast to explain the observations. So, but we want to stress some point here. In some case, this hot anomaly interacts the subducting slab very severely, and sometimes it may occur slab break-off like this. So then I will move to the second possibility, that is internally generated. As people know that in internally heated convection, there will be a hot patch just near the cold sinking material. So actually, Roma and others found that flow reversal in internally heated convection, like this, just you have to follow this and this way. So flow will reverse. So this occurs because of the existence of hot anomaly near the cold subducting material that will trigger the flow reversal. So that means hot anomaly close to the subducting slab may play a very important role in interpreting the slow velocity anomaly and possibly dynamics of subduction zone. So in order to estimate how much temperature anomaly exists, we constructed this kind of model, and we assume cylindrical geometry, and we took the extended Business approximation. And since we don't have much time, I will explain briefly. By changing the rate of internal heating, viscosity, and others, we obtained models which can explain plate velocity, heat flux, and etc. Then this is an example of result which shows the temperature anomalies. And actually, if you look at this result, you can see some hot anomaly close to the subducting cold material. And its magnitude is about 100 to 200 degrees. But it is in the lower mantle. But sometimes it occasionally moves upward. So if it goes up, the situation becomes like that of first case. So that means this kind of mechanism may explain the hot anomaly near the cold subducting slab. So actually, if you look at the recent tomography result, you may see some you may see a trace of slow velocity anomaly from the lower mantle. So we think that this kind of slow velocity anomaly or hot anomaly may come from the mid mantle. So we came to it. Oh, it's remaining time. Okay. Okay. We came to interested in backward calculations to see what happened in the past. So we did. This is a summary of backward calculations. We used the precise reversibility method by Ismail Zadeh and others with box geometry, whose size is written here. And we use the Newtonian viscosity mainly for the simplicity. And we estimate the initial temperature field from the seismic tomography. And we impose the surface plate motions on the top surface. I will explain more. Okay, this is a region which we modeled, just a dead box. This doesn't work. Just in the region of red box. And okay, so this is the initial temperature field. And temperature anomalies are obtained by seismic velocity anomalies of Obayashi and others. And we converted the seismic velocity anomalies to the temperature anomalies using the method by Goetz and others, and Ismail Zadeh and others. We added the background adiabatic temperature by Katsura and others to these temperature anomalies. Then we obtained initial temperature field like this. Okay, so this is a plate motion which we impose. Plate motion and plate boundaries. These are taken from the work, for example, by Seno and Maruyama. Okay, just we will move to the results. Okay, this is a result. This is a temperature anomalies, and just x-axis shows the time, and y-axis shows the depth. So present time is just right side column. So we interpreted this result like this. There is some common heat source, and it splits into ABCs somewhere here, and ABCs. Okay, maybe I should blow up the results. there is some common heat source, and it splits into ABC, small letter ABC, and capital letter large A, large B, C, large C. Large A corresponds to the backup of the Japan, and B is backup. Capital B implies exclusion, and capital A is just slow velocity anomaly under the Pacific plate. So I think we are thinking that during this kind of splitting, there might be a slab break off, and maybe hot material leaks through the slab edge or something like this. So in conclusion, hot anomaly in the mantle under the Pacific plate may have come from the mid-mantle thermal anomaly produced by the interheating and non-homogeneous effects, and it may have played an important role in subduction dynamics, such as backup opening. So I think just on time. Thank you.
Okay, thank you. Thank you very much. Other questions? One here too.
So it came from internal heat.
I think maybe viscous heating also.
And then how did it? Can you show me how it split from backup?
You mean
Yeah.
this reality? Actually, we impose the plate motion, so it's not fully dynamic. So we cannot see this kind of dynamic splitting, dynamic splitting or something like this. You understand?
Can you show me the figure before this one?
Before this one?
That one? What does it show?
Yeah. How can I say? You
So
can.
you see from the very deep, it comes up and then split.
Yeah, maybe. Yeah. you don't believe? Yeah. So we are suggesting that it may have a possible origin. Because we cannot do the dynamic calculation because we impose the plate motion.
Yeah, my question is, as you know, there is an increasing evidence that around the 410 discontinuity, there is a low velocity layer that people interpret as maybe presence of partial melting. And so, do you think you can explain with partial melting these observations, this low velocity anomaly?
Actually, I did not figure out quite well, but I think OS did such a kind of thing, and Bagley also considered such resistance of melt, I guess. So at least they concluded that it's common anomaly of 100 or 200 degrees. But I didn't check by myself. So.
Please.
I have a question. How about what's the role of the 660 if the thermal thing comes from the lower mantle? What's the role of the 660? If it comes through the 660, there must be something like raising of the 660.
But that model is rather constrained to the upper. Final model. Final model, backward modeling rather pay attention to the upper mass. So we are not so sure what happened.
Okay, I think there are no more questions, so we can proceed to the next talk.